Do you need to make a dilution and don't want to second-guess your math? Let's walk through the most common way to calculate dilutions that are often used at Quansis Biosciences. When you're making a fixed amount of a dilute solution from a stock solution, use the formula C1V1 equals C2V2, where V1 is the volume of stock solution needed to make the new solution. C1 is the concentration of stock solution. V2 is the final volume of new solution. C2 is the final concentration of new solution. Say you need 5 milliliters of a 0.25 molar solution from a 1 molar stock. Plug in your values and then solve for V1. In our example, you would multiply the 5 milliliters by the 0.25 molar concentration, then divide by the 1 molar concentration of stock. This will result in the volume of the stock needed. So 1.25 milliliters of the 1 molar stock solution should be added to the remaining volume needed to get us to 5 milliliters end volume, which would be 3.75 milliliters. If you are working with ratios instead of concentrations, dilution factors are the way to go. The formula for dilution factor is final volume divided by the solute volume. Since we are often trying to determine solute volume, we can rearrange the equation through simple algebra to say the solute volume is equal to the final volume divided by the dilution factor. To make 300 microliters of a 1:50 dilution, divide final volume by the dilution factor. 300 divided by 50 equals 6 microliters of stock. Now take the 300 microliters and subtract 6 microliters to equal 294 microliters diluent. Here's a quick tip. A dilution factor of 10 means 1 part sample plus 9 parts diluent. If the final dilution factor is too large or the volume is too small to pipette, use step dilutions. Use the formula dilution factor equals dilution factor 1 times dilution factor 2 times dilution factor 3, so on and so forth. Let's run through an example. You need 300 microliters of a 1:1000 dilution, but your smallest pipette volume is 2 microliters. Using the regular dilution factor method, this would suggest you pipette 0.3 microliters of the stock solution. Now, since our smallest pipette volume is 2 microliters, we will need to break down that dilution factor into multiple parts. With a total dilution factor of 1000, we'll break it into 1 to 10, then 1 to 100. Let's solve for the 1 to 100 dilution formula first and work backwards from our end volume of 300 microliters. Starting with the highest dilution factor and working backwards will ensure we make enough of our first dilution solution and use less stock volume in the end. We'll plug in the needed values into our dilution factor equation. 300 microliters divided by the dilution factor 100 equals 3 microliters. So we will need at least 3 microliters of the first dilution, the 1 to 10 dilution. Now we'll solve for the 1 to 10 dilution, which we know needs at least 3 microliters. Give that some buffer, and remember, we can't pipette less than 2 microliters. So let's make 30 microliters of a 1 to 10 dilution. Final volume equals 30 microliters divided by 10 equals 3 microliters. Now to perform our dilutions. We start with the 1 to 10 dilution by adding 3 microliters of our solute into 27 microliters diluent. Then move 3 microliters of the mixed 1 to 10 into 300 microliters minus 3 microliters, which equals 297 microliters diluent. To perform the 1 to 100 dilution, this results in our 300 microliters of a 1 to 1000 dilution. Serial dilutions are repeating step dilutions that are commonly used to build ELISA standard curves. The key formulas are move volume equals the final volume divided by the dilution factor minus 1. Diluent volume is going to be equal to the final volume. And total mixing volume equals diluent volume plus move volume. Let's run through an example with a 7.13 standard curve pipetted in duplicates. First, let's calculate the minimum final volume per step, which will also tell us our diluent volume. If we want to have 50 microliters per well, we'll multiply that by 2 for duplicates, which equals 100 microliters minimum volume needed per step. We're going to add an extra 20 microliters to compensate for pipetting error, which brings our final and diluent volumes to 120 microliters. Then calculate the move volume by inserting the final volume and solving the equation. This comes out to 60 microliters move volume. Now calculate the total mixing volume by adding together the diluent volume and the move volume, which in this example would equal 180 microliters. Let's prepare the first point of the standard curve, which is at least 180 microliters of the neat standard. Next, prepare 6 separate tubes with 120 microliters of diluent each for the remaining points. Transfer 60 microliters from the first point into the second tube and mix thoroughly. Then transfer 60 microliters from the second tube into the third, continuing this process through the remaining tubes to complete the serial dilution. Be sure to mix thoroughly between transfers. Whether you're using C1V1, dilution factors, step dilutions, or serial dilutions, the key is choosing the method that fits your volume and workflow. For more lab tips and assay guidance, check out our YouTube channel or visit quansysbio.com.